Battlestar Galactica, Bitcoin billionaire bourgeoisie.
We're just like,
Alliteration.
Should have had you come up with the title.
I'm good at that, dude. That's all. That's about it. Provide to startups is alliteration.
Sweet.
okay, ready? We actually have to do this quick because we're leave 6.
What time
Or
is it?
6:30.
What time is it?
No, we could go at
Now
6.
it's-
Hurry up, dude. Speed run it.
Let's go. This is
Let's go,
gonna-
let's go.
Yeah.
We're not going to get through all of this, but I will just
Let's
do
go,
the part
we're
that
gonna
answers
get
your
to your
questions.
Or
So this is what we're going to go over like 3 of these things. What BitVM is? Well, BitVM programs typically, BitVM is a virtual computer. And if you got, that's a real computer, BitVM's a fake one of those. But
64-bit.
typically we run BitVM programs off-chain. We do not try to run them, we try not to run them on Bitcoin, even though Bitcoin can actually do it. We have 2 counterparties in every BitVM contract. Both of them have a copy of the program. And if either party runs it wrong, they lose some Bitcoins because the code is also in a Bitcoin address. And that is the part that you are interested in, how to do that part. This is a little animation of how BitVM works. So we got Bob and Alice, or Alice and Bob are over here. They want to run a BitVM program together.
that's the sexiest I've ever seen.
Yeah, well,
You are the reason that Stable Diffusion.
we have Isekai. This girl has been transported into the world of BitVM, and she met Bob there. He's a blob Bob.
No face.
You need to explain Isekai.
No, we don't have time for that right now.
Yeah, I've only got 30 minutes to get through this hour-and-a-half presentation.
I want to see Mary now.
Oh, it's Mallory,
So
bro.
Bob says, hey, I made a Bitcoin address and it has an addition program in it. He gives her a copy of the program. She runs it and checks that it outputs the same Bitcoin address. And if it does, and if she wants him to run that program, then she says, great, I'm okay with using this Bitcoin address. Then they put some money into it together. Then they're happy. Next thing that happens is Bob computes something incorrectly. This is an addition program, and he's going to assert 1 + 1 = 3. Is that correct, anyone? Anyone say, no, that's not correct.
That's not correct.
That's not correct. So she's like, well, okay, if you're going to assert this, I want you to send me bit commitments for each number. We're going to get into what those are in a little bit. So he does. He sends her 0001. That's the bit commitment for the number 1, and another one for the other one. And then he's sending her the output bits. And this is what the addition program looks like in logic gates. And she can determine by passing those inputs into the series of logic gates exactly where it gets wrong, and it actually is there. Actually,
Where do they commit to the program? Do they commit to the program and the Bitcoin address, or?
Yes, the Bitcoin, and I will get, there's a bunch of slides on that, which
Okay,
is
cool.
the main reason why I'm going over this. So then Bob's upset, he got caught by Alice, and so she takes the money in this Bitcoin address, which I represent by having it move over to her side of the screen. And then she gets the money, she's happy. What can BitVM currently do? Well, it can add, when I made this thing, it could add, compare, and count. Now it can do TI-86 graphing calculator functions.
That's like FHE.
Yeah, so technically it can run Doom now, because Doom runs on it. No, I'm just kidding.
We should do that.
I know, I do want to run Doom on it, but I haven't translated it into my architecture yet. It can, in theory, you can run any converted program on Bitcoin. I see a way to do these 3 things. I've actually done a bunch of that one. I have not done either of these things, and
Wait. Why 2-player? Why not 3-player? Is there a reason? I don't
you
understand that.
probably could. You just have 2 verifiers. I was thinking you'd have the prover as 1 player and the verifier is another.
Yeah, it's
But if
too
you
hard
had,
to compute.
if you had 2 verifiers, you could probably do it with 3-player. I don't know. I'd have to think about that.
Because I'm not thinking of a game. I'm thinking of like NPCs.
Wait, why is the prover and verifier part of the game? Can't people play the game and the verifier just verifies the game ran correctly? Or is it?
Well, but then any player could make the prover lose money if the verifier does it wrong. I don't know. I'd have to think about it. You probably can expand it to 3-player games or N-player games.
Okay, I was just asking because 3-party.
I certainly haven't made anything work outside of a 2-player context. That's what I've done.
Okay.
You could probably do it with more players. Some of the limitations of BitVM are, well, it has a bunch of limitations, but I don't want to go over them because we only have very limited time. This is a logic gate. This is a very basic computer made of a logic gate.
Nice cylinder.
Huh? There's an AND gate right there, and there's a battery over there that's going to supply power. If we take a wire and connect it to the battery, there is no electricity flowing in that wire because it needs to be connected to the bottom of the wire, of the battery. That makes a complete circuit. Once we do, electrons start flowing from the positively charged end to the negatively charged end. And now, if we connect anything on this, any of the wires connected to this logic gate to that, they will light up. So, for example, if we connect the top one, it will light up, but because it's an AND gate, This one will not. You know what needs to happen for the other one to light up?
Yes. You need to connect both.
You need to connect both. So here we go. Now it's lit up. You guys see how an AND gate works? This is how we program BitVM, or at least this is how I do it. This is not how any sane person does it. It's just me. These are the main logic gates. I don't think I need to go over this because you guys are all programmers. You all know the logic gates.
But
But
just use ChatGPT.
this one is the most important one. NAND can simulate all of the other ones by hooking a bunch of NANDs together. But although we use it a lot in the BitVM white paper, my implementation of BitVM only uses it once. There's only one NAND gate in my CPU. This is an adder. This is the program I was showing you earlier where Atlas found that he did something wrong, except that was a 4-bit adder. This is a 2-bit adder. If we connect the AND gate and the XOR gate, they're both on the same wire to this battery, then we will get 1 as an output, because only the XOR gate takes an exclusive, it only fires if one and only one of the wires is on. That one fires, so we get 0, or we get 0, 1 as output. And that means we have connected one wire, and it's telling us we have 1 as an output. If we connect the other wire, we still get 1, because the AND gate needs both, so it's not going to fire, but the XOR gate only needs 1, so it'll fire. And if you do connect both, the AND gate will fire, so we get 1, 0 as an output, meaning we've connected 2 wires. It's counting how many wires we've connected to the battery. And the XOR gate won't fire because XOR needs only 1 of these wires to be on, and they're both on, so it puts out a 0. You guys with me how we can start to do computation here?
Yes.
This is an 8-bit adder, which is much more complicated. It's the same thing, just writ large. And this is an Intel IBM CPU. So somebody took this silver plate off of their Intel laptop, or I don't think it was a laptop, but some other device. And they popped it off and did an electron microscope scan of the results. And if we zoom in on it, zooming into this part, and zooming into that part of that part, and zooming into this little corner of that part, this is an AND gate, and that's what it looks like in a transit when it's mechanically created using transistors. So your computer, every computer, is just a series of logic gates hooked up together in a massive complex like this. That's what a computer is. And since we can do logic gates on Bitcoin, we can recreate a computer on Bitcoin and then run any program in it. Would you guys like to see how we do that?
Yes.
Yeah, that's what we're here for. This is an anatomy of a Bitcoin transaction. This is a standard Bitcoin transaction, not a BitVM one, and I've color-coded it. I've taken this from the book Mastering Bitcoin, and there are a bunch of parts in here. I can't go over all of them, but this is like a transaction ID from the previous transaction that put money into whatever Bitcoin address you're spending from. This here is, this number here that is a 2, says we are sending money to 2 Bitcoin addresses. One of them is here in blue, the other one is here in red. And the red part up here is the signature that allows us to send money away from whatever address it's currently in. That is that's the most important part here. In fact, this is the signature, and then this is the public key that currently has the money. So here's the public key that currently has the money. Here's the signature that is saying, I own this public key, and therefore I'm allowed to send the money to the 2 addresses down here. So that's called, this part is the most important part of a Bitcoin transaction, and it's got a whole bunch of names. Sometimes it's called the redeem script, sometimes it's called the script sig, sometimes it's called the witness script or the witness stack. Bitcoiners give this thing a lot of names because we use it all the time, and everyone comes up with their own name for it. Bitcoin can also do scripts. It doesn't only have the ability to do pub keys and signatures. It can also do scripts. So here, I'm actually doing a sum to 3 program where I have, there's like a legend down here that says what each thing is. But there are 6 bytes in this program. The number 51 in Bitcoin script is the number 1. I know. Why is 51 1? Because Satoshi did it that way. And then this number 52 is the number 2 in Bitcoin script. And we are saying that you need to provide 2 numbers, 1 and 2, that sum to, sum to the number 3, which is 53 in here. So the program is 93, 53, 87, and 93 means add these 2 numbers, and the result has to be equal to, that's 87 is off equal to 53, or 3. So the person spending this has to supply 1 and 2, or he could do 0 and 3, or he could do -1 and 4, just 2 numbers that sum to 3, and then he is allowed to spend this money. When we create the Bitcoin address is actually a hash of the program. When you send money to a Bitcoin address that is not pubkey based, but based on a script, this is what you hash, and you send money to this hash. And then when you redeem it, you have to show what program hashes to the hash of this. And then you have to supply arguments to that program that make it return true. If you do that, then you're allowed to spend the money.
So,
What's up?
basic question: do you encode every number as 3 bytes in Bitcoin script, or is that just like OP1, OP2? Are they both by convention 3-byte numbers, or can you make them different size numbers?
You say the number so up 1 is just 1 byte.
But why do you specify 6 bytes for the input right before the script starts?
So the whole it's 1, 2, 3, 4, 5, 6.
Oh, that's the entire program size.
Yeah. The program is 3 bytes, and that's what this signifies.
Oh,
The
got it,
inputs
got it,
are
got it.
2 individual
6
bytes.
bytes, okay.
Yeah, and so the total is 6
Okay.
bytes. You good?
Okay.
So that is how we do scripts in Bitcoin. If we wanted to do, well, there's a whole bunch of scripts that Bitcoin supports, script opcodes. These are the ones that I mostly use, and in particularly this line, this is what I built the little calculator in. So I use these a lot. And those are all supported by Bitcoin script, which is great. And you can use these, you can combine them to make any sequence. You can make an entire CPU with it. Okay, so to make an AND program, if we wanted to just do the AND that I showed you in the beginning, the Boolean AND, we would take a script, which is just an array of opcodes. We would do bool AND, that's what we have in there. And we would take that script and hash it, and this is the resulting Bitcoin address you get. So you can send money to this, and then you have to supply, if you want to spend it, you have to supply a 1 and a 1 as inputs, because that will produce a 1, and that's when there's a 1 on the stack, Bitcoin says that's
So you don't have to
that's good.
You don't have to use a private key.
You don't have to use a private key for
Use
this.
as long as you know how to run the program.
In BitVM, we actually do use private keys as well, but that'll come later. This is if you just wanted to have it say you need to supply a 1 and a 1, Boolean AND, and then that'll run.
This is actually working on mainnet, right?
This is actually testnet, but you can run this on mainnet. You would just need to change this to mainnet, and then it'll be on mainnet. Yep. So this is me doing this is what the transaction would look like. It's only a 4-byte transaction. 9A is bool AND. And the inputs are just 51 and 51. It's 1 and 1. And that'll make it produce a 1 as output, and that's what Bitcoin wants. If you did a 50 and a 51, then it would be false, because in the AND, both of them need to be 1s, and you didn't do it. So then you wouldn't be able to spend it. Okay. A few problems with trying to build a CPU this way. One is, well, I can't go over this one, but the main thing is that there's not enough space. We only can use 400 kilobytes of space in a Bitcoin transaction, and if we go over that, nodes won't relay it to miners, and miners won't mine it unless they're like running custom software. So you have to be really careful not to go over 400 kilobytes, and if we tried to put the entire script in there, it would be, for a calculator I mean, it would be too big. It would be more than 400 kilobytes, so we can't do that. But we have the solution over here, which is this tree. Taproot gives us the solution that lets us bypass the limits that Bitcoin put in and get rid of it. And he knows all about bypassing the limits inherent in Bitcoin, because that's his specialty. So how does Taproot work? Well, because of Taproot, we can have many scripts in one Bitcoin address, and we give each script an identifier. We actually put them in a little tree structure like this, and the leaves of the tree are where all your scripts go. So for example, you might say this one is just a regular pub key, and if you know the pub key, you're allowed to spend the money. But this one might be op AND, and if you don't have to have the pub key, because you can also do this one, and if you just know how to make op Boolean AND, you can supply 2 1s, and you can make it go. So we have the ability to put a whole bunch of different scripts in a Taproot address, and when we do that, we Merkleize them. We make the Merkle tree out of them, and we take the Merkle root right here, and that is the hash that you send money to. Then in order to spend the money, you have to supply a proof that whichever script you're spending, let's say it's this one, you have to supply a proof that this script is in the tree somewhere, and then make that script return true. So this allows us to take this big calculator that's got many, many, many scripts and just make a whole big Taproot tree. You know how many tap leaves you're allowed to have in a Taproot tree? 2 to the 128.
Yeah.
Yeah! You know how big that is? That's like the size of the key space of Bitcoin, of Bitcoin's elliptic curve. It's like really, really massive. It's more. There's no program that's ever been written that has more than like 2 to the 40 lines of code in it. So this means we can encode an entire program as a series of tap leaves and put an entire program on Bitcoin. There's a lot more, but I think it's time for us to quit.
No.
I guess I have 15 minutes left, don't I? Or okay, so we'll keep going. Normally, when you have a tap script, it was designed so that the person who's spending the money would pick which tap leaf they want to spend from. You know, like if they have the public key, for example, then they might do that. Or if they're like, well, I just happen to know that 1 and 1 will make Boolean return true, so I can use this one instead. Normally, the sender is supposed to pick. But Rob and Linus figured out a way to let an alternative party, a counterparty we call them, to let somebody else pick which script you have to run. And he did that using hash locks. So we also use this for how we transfer state from one Bitcoin address to another. But how we do this is with hash locks. Do you guys know what cryptographic hashing functions are? Raise your hand. Everyone raise your hand.
Like, what is like SHA?
No, just raise your hand.
Oh.
Your hand's not raised. Raise it. Raise your hand. Raise it. Put it up. All right. Now lower your hand if you don't know what SHA-256 hashing functions are. Okay, everyone knows. Great. So I don't have to explain what those are. All right. But we use them in BitVM. And so we're going to have an address that allows you to spend the money, or a script within an address that allows you to spend the money. If you can reveal, but in order to spend the money, you have to reveal one of these two preimages. You have to reveal the preimages to one of two hashes.
Is the preimage just like the hash input?
Yes, the preimage to a cryptographic hashing function is the data that you put into it, and then the hash is the value you get out.
Okay, well that's okay.
Yeah.
Fancy math language.
Yes, it is. We use fancy math language on BitVM.
Okay.
Okay, so then what we do is we have Paul and Vicky, we call them when they're two people participating in BitVM. We have them create a multi-sig Bitcoin address where not only do you need to reveal a preimage to move the money, but you also have to have both of them co-sign that transaction. But we do that in advance. In advance, we have them co-sign a series of transactions that send the money from address A to address B to address C to address D, and each of these addresses encodes a part of the program, and so we can use this to transfer state by saying we make a preimage that represents a 0 and a preimage that represents a 1. You have to reveal one of them in order to not lose your money. And once you reveal one, we replace that preimage that you revealed with the corresponding 0 or 1. And then we have 0 or 1 in that Bitcoin address. If we use the same hashes in address B over here, then address B suddenly knows what happened in address A. He knows if you revealed the preimage for 0, he knows that, and you now have that data in address B. So this allows us to take the program, which can be very, very large, and smoosh it into a whole series of Bitcoin addresses, and then do that, which is great. What's up?
Also high five. Is this why it's 2-player only? Because of these two preimage? You need a third preimage to do 3 players or not?
You could do only the prover has to know the preimages. Okay. He's the one who has to reveal it.
Sorry. Keep going.
Yeah. I think you could do it with 3 players. I just never done it. Okay, so if we add in all of that stuff, then, well, our script gets a lot bigger. Before it was just bool and, but now we're going to have something called a hash lock on top, and the hash lock ensures that Paul can only spend money from a given logic gate. If Alice reveals a preimage, a secret that only she knows, that tells Paul which logic gate he's going to spend the money out of. And so he cannot just pick one. It has to be one that she allows him to do. And this lets us set up a challenge and response game. She can challenge him and say, I want you to show me logic gate number 7. And if you can show me what were the inputs and outputs of logic gate number 7, then you can proceed into the next Bitcoin address, into the next part of the challenge response game. So the next SHA-256 thing is the one where Paul reveals either a 1 or a 0. And so if he reveals the hash that corresponds to, the preimage that corresponds to this hash, we drop a 1 on the stack. And if he reveals the other one, then we check if it equals this hash, and if it does, we drop a 0 on the stack. So that's how he can reveal 0 or 1 in each, whenever she challenges him. Then in this case, we're doing op not. I changed it from op boolean. I forget why. I think because I wanted it to fit on the slide. So we're doing an op not here. So it's going to invert. If you revealed a 0, we're going to invert it to a 1. If you revealed a 1, we're going to invert it to a 0. We check if it equals the output. So he has to say, whatever I'm revealing, if I revealed a 0 and I'm doing an op not, he also has to reveal a hash that corresponds to a 1 here. And if he reveals the 0, then the not will fail. It will say, no, if you revealed a 1 and then you're saying or if you revealed a 0 and you're saying it comes out as a 0, that will fail because op not will say that's wrong. A 0 should turn into a 1, not into another 0. So this allows you to enforce logic gates on Bitcoin, and the requirement is that Paul, or the prover, has to say not only what the inputs to each logic gate are, but also what the outputs of each logic gate are. So that is what that looks like. And then if it works, if he successfully reveals the right preimages, then we use Paul and Vicky's pub keys together to send the money to the next Bitcoin address, and we continue the challenge and response game. So this is what BitVM looks like. It's a bunch of tap scripts that all have this in them. At least this is how I do it. But this part's different. You can use any logic gate in here, and then Vicky can force Paul to reveal the inputs and outputs to any series of logic gates. Then what we do is we need to prevent Paul we need to hook them together. So, what's up?
Sorry, I'm a bit lost. So the program itself, you commit to the program with these preimages, but
Yeah.
why is the money sent if Paul Casholi knows essentially the code of the program? Shouldn't it be like sent if it shows that he computed the program correctly or something like that, or I'm not really. I'm just a bit lost in general.
I'm sorry.
No, it's not your fault.
It would be better if I had more time to go through this all. So the Bitcoin address has a tap leaf for basically every line of code in the program, every line of code in all those logic gates. And Paul, hopefully, he knows exactly how to, whatever Alice wants him to do. Let's say it's show me that you won a poker game. Hopefully, he has actually done that, and so he can show her the data for that, and she can run the data he gives her through her copy of the program. And if it's good, then she's like, no challenge response game is needed. You didn't cheat. You did it all correctly. So you should just let him have the money. If she finds out that he did cheat, then we initiate challenge response. She finds out which line of the program fails given the inputs he provided and the outputs that it doesn't match. She finds which logic gate it failed at, and then she challenges him to reveal the hashes, the preimages to the hashes that made that logic gate work. And so he has to provide something, otherwise he loses his money. And if he so I hope you're a little bit more on board now because I'm gonna because I'm gonna go through the rest of that here. We need to figure out how to hook these logic gates together because of reasons. So because a program is actually a circuit that has them hooked together. We need to recreate a circuit in Bitcoin script. We need them to be hooked together the way they are in an actual computer. So how we do that is we create a pair of preimages for this input to this logic gate, AB, a pair of preimages for this one, CD, a pair of preimages for this output gate, E and F, and a pair of preimages for this output gate, G and H. So Paul, when he's revealing something, let's say he's going to do 1 and 1 as the inputs here. He's going to have to reveal A and C, because those are 1 and 1. And then he's going to have to reveal E, because that's 1 here, and 0 and H, because that would be 0 down here. That's going to be what he has to reveal for those in order to not have Alice take his money. You guys with me? Some of you, he's nodding. The rest of you have dead eyes. Looks.
So these preimages are.
We're following.
But it's like, is it just the preimage 0 or 1, or is it essentially the preimage corresponds to like a block of code, or like?
It's just random. There's the random 32-byte values. But if he reveals the preimage that we've designated for 1, then we replace that preimage with 1 on the stack. That's what.
Is that pretty redundant if the only value you can output are 0 and 1? Is that pretty?
No, but this is not the preimage for the number 1.
Okay.
This is just if he reveals the preimage that hashes to this value, then we check op equal. That destroys it, and then we drop a 1 there.
Got it.
So we get a 1 on the stack.
And this is the pre-image for a line of code in the program, or
This is-
essentially where line of code is equal to like what you showed before, which is
Each line of the program is just a logic gate and a hash that represents, or 2 hashes rather, one that represents whether he's going to reveal a 0 or a 1, and then he picks which one he's going to reveal.
so the hash, the hash represents whether you will
Yeah.
reveal.
There's a hash for 0 and a hash for 1,
Yeah.
and he has to reveal the pre-image to one of them in order to set that wire equal to a 1 or a 0.
That OP shot thing you got on that last slide. What was the pre-image for that? You had some OP shot thing with something like that. What was the pre-image for 4721? What's the pre-image for that?
I don't know what the
I think that's what
pre-image
he's trying to figure that out in his head. Right?
Yeah, it's like you showed this like representation of a program before where it was like 06, 51, 52, 03,
Yeah.
and then is that the program? Is that the program that you're hashing, or?
This program here. It's actually there's 3 slides. This plus this is one of the scripts in one of the tap leaves. And on the witness stack, if I go back to this one, so the program is going to be kind of long. It's not going to be just 1 byte right here. It's going to be a long program because there's a lot of stuff in there. There's hashes and other things. On the witness stack, when he reveals the information that goes into this, he's going to supply 2 pre-images, right? Instead of a 1 and a 1, he's going to supply the pre-image that corresponds to
I don't
this
understand.
hash.
Is there like a 1-to-1 mapping between the pre-image of what and
Can I try?
and what?
Yeah,
This
you
is-
go ahead.
Yeah, it's called commitment, right?
Yeah.
You understand commit, right? It's like, let's say I have, coin, right? I put it here, and then I use my hand to cover it, right?
Uh-huh.
That means I cannot change after the fact, because otherwise it's not commit.
Yeah.
And then at the same time, you cannot see it, because if you look at this hash, you don't know what is 0 or 1. You don't know, right?
Well,
But
there's
I
only 2
cannot
values,
change
0
it.
Well,
or
no,
1. So for
No, no,
looking
no,
at this-
it's equivalent, because I have only 2 things. Either hash to this, or
He
the
has
next
this.
one.
He
I
has-
cannot equivalent after that. I
He
cannot
has
change.
to reveal either the pre-image
this or
that
that.
hashes to this value or the pre-image that
Either
hashes to
hash
this
or
value.
tail. I cannot
Yeah.
change later. So this is the same.
No, I understand that. Like you're
It's
saying
just
this,
commitment.
that this is like
It doesn't really matter.
This is the pre-image of 1, or
It's
like
not.
You
No,
don't know.
it's just
That's
a
the
random
whole
value.
point.
Yeah.
If you can figure out,
Yeah, that's
you
it.
know
Yeah.
it's head or
Yeah.
tail.
It's
It's
just,
not going
it's
to
just a
work.
random value. It's a
Yeah.
random. I think it's a 32-byte string is the pre-image, and it hashes to this 32-byte value. And if he reveals that pre-image, then we get rid of this and we drop a 1 there.
but what's
It's
that?
head.
What's the point of this? Shouldn't it be committed to something? Like why are you committing to a random value?
It's a gate. It's a binary gate, right? It's
Yeah.
0 or 1. The wire can only be 0 or 1. It's binary.
We don't care what the value is as long as it's not guessable. Because if he actually did the number 1 was his pre-image, then she could detect that in advance. She already has that pre-image, and she could make him fail the transaction by
Right.
putting in false data.
It's
Oh.
a signature. The secret is a secret private key,
Uh-huh.
and like the thing you're doing is signing. So you
Got
need
it.
enough entropy in the private key so they can't figure out what it is ahead of time.
Oh, I see. You're kind of showing that you ran the program. Like it's like a way of showing providence that you were the one that ran it, or else you wouldn't be able to
Well, like
know the
otherwise
pre-image.
the
essentially.
verifier could punish you, right?
Yeah.
Like, if the verifier could figure out the pre-images ahead of time, then they could pretend like you had equivocated.
Got it.
So we-
Oh, I see what you mean. Yeah. Okay. I see.
Great, he's on board.
Yeah. Yeah.
Sweet.
Yeah.
All right.
It's clearly the only one that was lost there.
So
Ever.
if we need to, let's suppose that in our addition program over here, it needed to flow into some other logic gate over here. What we do is, since he had to reveal E and F, or E or F for this logic gate, and G or H for this one, we just reuse them in the next line of code. We reuse those same hashes in the next tap leaf, and then Alice knows what the inputs to these are. He doesn't have to reveal them again. She knows that if you reveal E here and H here for 1 and 0, then in this logic gate she can just reuse those pre-images. And so we've hooked 2 logic gates together, or 2 series of logic gates together, just like they're done in a real computer, but we can do that on Bitcoin. Okay, so whenever we do a challenge, we also have to have a way to respond. So we have challenge and response. Alice challenges. She says, "Hey, show me the inputs to this logic gate," and Paul responds. He has to pick whichever. So Alice challenges by revealing the pre-image to one of the tap leaves that she wants him to reveal the inputs for. So he reveals the pre-image to that hash, and then he reveals the ones and zeros that go into that logic gate. If Vicky never challenges, like if she's too slow to actually give him a challenge, then Paul just gets to take the money. The time lock expires. It's like Vicky saying, "You're good. You didn't cheat." If Paul equivocates, if he reveals in this step that it's an E here, but then for this one he reveals an F, there's a tap script that lets Alice take his money because then he has cheated. He has tried to say that it was that the value switched halfway through the program, which is not okay. So she gets to take his money if he does that, and if all goes well, if he gives an accurate response to her challenge, then she can challenge again. So we do challenge and response until you get to the end of however many steps it takes to figure out whether he accurately ran the program or not. Which for each program is like a way to find out how many steps you need at maximum in order to do that. So the last thing in BitVM, the thing that I have not implemented, but Robin's team has, and the Citria guys have implemented this, is called bisection. So in order to do this efficiently in Bitcoin, we start at the end. We start at the last logic gate, which is going to give a true or false value. And Alice challenges Paul, I think, do I have slides? No, she challenges him to reveal what the information for here is, for this last gate. So let's suppose he reveals that it was a 0. For NAND, that means the inputs both have to be a 1. So she checks, if in her copy of the program, she has a 1 and a 1 here, then she shouldn't have challenged him. Because if she got a 1 and a 1 here and it came out correctly as a 0, then she's like, why would you challenge that? That means the program ran correctly. And he can win the challenge then. So what she does is, she only challenges if she has different values here. If she has like a 1 and a 0 here, and he revealed a 0 as output, he should not have. He should have revealed a 1 as output. So she only challenges if she gets a different result from him. And then she knows that if he reveals a 1 and a 1 here, then she's like, this was supposed to be a 0 though. Because my copy of the program showed that at this stage you get a 0 when you input the data that you provided me. So that's what she challenges next. She says, this one we have different values on, so I challenge this gate next. Show me what you put in as inputs and outputs for this gate. So Paul has to do that, and eventually you get all the way back up at the top. And if Alice and Bob got different results, then one of them ran the program incorrectly. So whichever one ran it incorrectly, it loses. They either have to show logic, they have to show inputs that don't produce the expected output, or they have to equivocate and lie. And whichever one does that loses the money and loses the game, and thus you've done an entire program or an entire computer or whatever you want, all in Bitcoin, all on Bitcoin.
And each line of this program is committed to in the address. You're switching addresses for every step of this, or is it essentially a leaf in this taproot tree that represents?
Each logic gate is one leaf in the taproot tree.
Got it. You have to provide a Merkle proof essentially opening the tree at that point.
Yes, you have to. Every time you do one of these taproot transactions, you have to provide a Merkle proof demonstrating that your logic gate was in that tree. If you're using logic gate.
And how do you enforce the ordering? Like, how do I know that you have